Hello everyone. In the previous session we have discussed the concept of function of bounded variation. So in this session let me continue few more theorems which is important as per exam point of view. So either they can ask statement directly or they can ask lebesque theorem, state and prove lebesque theorem. Fine. So in most of the examination they have asked only the statement. So if f is increasing and real valued function defined on a closed interval ab, then f is differentiable almost everywhere, and the derivative f dash is measurable. Furthermore, we have to prove integral from a to b f dash of x into dx is less than or equal to f of b minus f of a. So we are going to prove this by using the concept of Dini derivatives, as I explained the concept of Dini derivative in the previous session videos. Please go through that so that you will understand the concept of Dini derivative. So in order to prove this, let me consider a function f which is differentiable. So we have to prove the function f is differentiable, right? So to prove that f is differentiable as per the theorem statement, to prove f is differentiable. Fine. Now let us consider a function e in terms of Dini derivative in such a way that a set E contains an element x which is inside the open interval ab, and further Dini derivative of f of x less than positive derivative of f of x. Fine. So now we have to prove that measure of this set is equal to 0. So in order to prove measure of set E is equal to 0, we are going to define two rational numbers u and v in such a way that E of u comma v is none other than x belongs to the set AB. Whatever the set I have considered for E, I am going to rewrite for the rational numbers u and v. So x belongs to AB. The assumed rational numbers u and v will be in between these two Dini derivatives, that is d of f of x less than u less than v less than d plus of f of x. So whatever the function that is E I have assumed, I have rewritten it by defining the rational numbers u and v. Am I clear? Now clearly E can be expressed as product of u with respect to uv and u of u comma v. Now we have to show that m star of E is equal to 0, right? So it is equivalent of proving m star of E of u comma v is equal to 0. So in order to establish this, we need to prove m star of E of u comma v is 0. Fine. Now let me take m star of E of u comma v as alpha. Then for any epsilon greater than 0, there exists an open set O such that which contains E of u comma v. Suppose if I have open set O, E will be inside this O. Then clearly when you are going to take measure on this set O, which will be always less than measure of E of u comma v, that is E of u comma v is containing in O. So m star of u comma v will be greater than m star of O plus epsilon. If you are adding some extra quantity to epsilon to this measure, you will get always measure of O is less than this value. Fine. Now let us take an element x. Randomly I am going to choose an element x which is inside this set u of e comma v. I am going to consider this set. So whenever you are going to consider an element in this set, obviously this condition will be satisfying, right? That is d of f minus x, that is negative value. D minus of f of x will be always less than u. Then if this was the case, there exists one small quantity h such that x minus h comma x will be subset of O. So this element will be inside this open set O such that which always satisfies the condition when you are going to take difference of the function, that is f of x minus h will be less than u into h. Then let me consider one more function, say tau, in such a way that it contains a difference of x minus h and x. I am going to consider all these collections as tau, which covers E of u comma v. So this is a collection of set which covers E of u comma v in the sense of vitally. I have explained the concept of vitally, so you just go through that. So from the definition of vitally covering lemma, I can write when you are going to take measure of the set uv and the difference I is equal to 1 to n of I will be less than epsilon. All the measure theory is entirely abstract. You don't have any way, you need to practice. That's all. Fine. Now, since it is less than epsilon, where I is none other than xi minus hi comma xi, where I value will be, that is generalizing case. So I am generalizing it for the, so this term I am generalizing this for I is equal to 1 to n. Now I am going to take summation of this equation. I mean, when you're going to take sum of all the values of n for this equation, I can write summation I is equal to 1 to n f of xi minus f of xi minus hi, generalizing and taking the summation, is always less than u as it is, and h is the varying quantity. So let me take summation I is equal to 1 to n hi, and further this value will be less than u into, this is none other than measure of O. So measure of O, and further I can write this as u into measure of O is none other than smallest quantity, that is alpha. Why? Because I have already assumed that measure of E of u comma v is alpha. U comma v is one of the set which is inside O. So I can write this as measure of alpha plus epsilon, one extra quantity. So let me take this as equation 1. And now let us define a set A as E of u comma v intersection with union of all the intervals of I of I. INT stands for intervals of II. Fine. Now let us consider an arbitrary element y which is inside the set A. Whatever the set I have assumed A, I am going to consider an arbitrary element y which is inside this A. Then if that was the case, y is also belongs to E of u comma v, and y is also belongs to this interval. Since y is an element of A, so y is also in E of u comma v, and y is also in interval I of I. Fine. Now, since we already know that since positive derivative, that is Dini derivative of f of y is greater than v, then there exists, as per the definition, then there exists a small interval such that y comma y plus k will be subset of II in such a way that it will be satisfying the same condition, that is f of y plus k minus f of y, that is difference of the function interval, will be greater than v into k. Now let me take, since here I have considered tau as a collection of all the elements, now let me take tau star. For the second case, tau star be the collection of y comma y plus k. Here x minus h comma h, here y plus k comma y, or y comma y plus k, and this will be the vitally cover for the set A. Vitally cover for set A. This will be the vitally cover for the set E of u comma v. Fine. Now as usual, as per the vitally covering lemma, there exists vitally covering lemma we have to apply, right? So there exists an interval, say I1, small j, or let me take J1, J2, why? Because all the intervals I are chosen here only for the first case. So let me take I1, I2, I up to so on, J1, J2, Jm will be the interval which satisfies the condition that m star of A minus union of I is equal to 1 to m, Ji will be less than epsilon. That is, whatever the set I have assumed A, if you are going to take measure of this set A with difference of all the interval is always less than epsilon. And since we already know that since m star of A is greater than alpha minus epsilon, right? If you subtract, if m star of A is less than epsilon, less than alpha, if you subtract some value from the alpha, it will be greater than alpha minus epsilon. Now, from this definition, it follows that the above equation can be written as m star of A minus will become intersection union I is equal to 1 to m, Ji will be greater than alpha minus some quantity 2 into epsilon. Fine. Now, I am going to take sum of all these values over the, I am going to take summation over all the values of j is equal to 1 to m, f of yj plus kj minus f of yj will be less than, or let me write one more step, will be greater than v times summation k is equal to, j is equal to 1 to m. Why? Because v is constant, somewhere I have done, right? So for this value I have taken summation, no? So here u is constant and h will be varying, so I am taking summation for that. Similarly here v is constant for in this step, so k is varying, so I am going to take summation for it into kj. Again it will be greater than v into kj is none other than alpha minus 2 epsilon. Why? Because kj is containing elements of this form, obviously it is greater than alpha minus 2 epsilon. Fine. Now, since all the j's will be subset of ii's. Ii's are the intervals of x and hi's, whereas j's are the intervals of y and y plus k's. So, since it is subset, thereby I can write summation j is equal to 1 to m f of previous step yj plus kj minus f of yj will be less than or equal to f of xi minus f of xi minus hi. So this is the values of ii. Why? Because it contains the intervals of ii. This is the values of ji. Since jj's are subsets of ij, whatever the whatever the elements you have inside, they will be always less than. Subset will become less than or equal to. Fine. Since it is in the theorem statement itself, it is given that f is an increasing real valued function. So I'll just write here. So since f's are increasing and real valued function, therefore I can write that for I is equal to 1 to n, we can write summation. I have already written this, so I'll just continue the same. See, for this step, for the LHS value, I can write it as v into alpha minus 2 into epsilon, which is less than, what is the value of this? I have already arrived, that is u into alpha plus epsilon. U into alpha plus epsilon. Here I have written from equation 1. See, this entire value is less than u into alpha plus epsilon. So I have substituted the value here. See, from equation 1, this term is none other than u into alpha plus epsilon. So this term is none other than v into alpha minus 2 into epsilon. That is what I have substituted. Since epsilon is greater than 0 and it is arbitrary, so we can neglect it. Thereby I can get v into alpha is less than or equal to u into alpha. Epsilon is arbitrary quantity, we can neglect it. Since u is always less than v, this implies that alpha will be equal to 0. Since if u is less than v, we can write alpha is equal to 0. Now, m star of e, alpha is 0 is none other than m star of e is 0, right? Why? Because I have arrived that, see here, m star of e comma uv, m star of u comma uv, e of u comma v is alpha. What is the value of alpha? Alpha is 0. If you substitute, you will get m star of u comma e of u comma v is 0. So if this is 0, we can say m star of e is 0. So this is what we have arrived. That is, measure of a set e is 0. E is none other than an element which contains this form. I'll just substitute one. I'll write one more step. M star of set x belongs to a comma b such that any derivative of minus fx less than fx will be equal to 0. That is, I have just replaced the e value in m star of e is equal to 0. Meaning of this statement is any derivative of fx, negative derivative of fx will be equal to positive derivative of fx. That is, both are equal. Why? Because the measure is equal to 0. Both are equal on the assumed interval ab. Similarly, we can prove that d positive of fx will be equal to d negative of fx, and whatever the 4 inequalities I have explained in a dini derivative, you just go through that. We can prove that all are equal. So similarly, we can prove all these 4 inequalities of equations of dini derivative. Since we have proved it is true for one, it is obvious for all the derivatives. Implies that derivative exists, that is dini derivative, that is f dash exists. If this is true, we say that f dash exists on AB. So a part of a theorem is finished. See here, if f is differentiable, meaning is f dash exists. Now we have to prove that this inequality also holds good. Let me prove. Anyhow, theorem is lengthy. No way, you have to practice. So we have arrived that f dash exists, in the sense differentiation of a function f dash exists. So but from the definition I can say definition of the derivative, limit h tending to 0, f of x plus h minus f of x divided by h exists. So let me take this function as, say, g of x. Fine. Differentiation, since f dash exists, in the sense differentiation definition I have written, so let me take that as g of x. For generalizing case, I can write gn of x is equal to f of x plus 1 by n minus f of x divided by 1 by n. For generalized case, I have replaced, h is a small quantity. Fine. So I have replaced h with n for a generalizing case. So as n tending to infinity, this will not be differentiable. So that is why I have replaced it as 1 by n. Now what I am going to do is, I am going to set f of x is equal to f of b. Since f is an increasing function, right? Why? Because it is given in the statement itself. F is an increasing function and gn is also sequence of non-negative measurable function, right? Why? Because we have expressed gn in terms of fn, meaning is gn is also converging to g almost everywhere. Then we can apply Fetus Lemma. I have already done this. Therefore, by Fetus Lemma, I can write integral from a to b of the function g will be less than or equal to limit infimum of n tending to infinity a to b of gn. Fine. Now I can write this as limit infimum of n tending to infinity. N I can take outside. So gn I am going to substitute f of x plus 1 by n minus f of x. I have just substituted this value. Fine. So gn of x value is there. No, I have just substituted 1 by n. I have shifted to numerator. So I have written n here into dx. Now the limits are from a to b. I'll just continue here. So what I'm going to do is I'll just split the integral sign. So I can write limits infimum of n tending to infinity, n as it is. Now I'm going to split this integral term, that is a to b, f of x plus 1 by n into dx minus integral from a to b f of x into dx. I have splitted this integral for both the terms. Now further I can write this as, since I have splitted the minute when you split the integral you can write it as equals. So which is equal to limit infimum of n tending to infinity n of, now I can change the limits from a of a plus 1 by n, b plus 1 by n of f of x into dx. Fine. If you integrate this function and if you substitute the limit, if you simplify, you will get back this. So we can write as per the property of integration, we can write like this. Both are equivalent. Minus integral from a to b f of x into dx. Now, limit infimum of n tending to infinity n into, now let me rewrite this integral by changing the limits as per the property of integration. So I'll just interchange the limits. So I can write b plus 1 by n. I'll just write this integral, limit here. So I can write this limit here, a plus 1 by n to a f of x into dx. Now again I can write this as, which is less than or equal to limits infimum of n tending to infinity of n. So after simplification you will get f of b by n minus f of a by n. You just substitute the limits and if you simplify this you will get this. So as limit infimum of, since n and n get cancelled, if you apply limit infimum of f of b, it will be f of b only. Why? Because it is independent of n, minus f of a. So what is the value you have in LHS? It is a to b of function g. G is another than derivative of a function f. So I can write this as a to b of f dash of x into dx. That is a to b of f dash of x into dx is less than or equal to f of b minus f of a. And this is important theorem. Please do practice. Anyhow it is lengthy and abstract, no way. Measure theory is itself abstract. Measure theory and complex analysis, majorly abstract subjects you have. Even up to today we don't know where is the application of this particular subject properly. So no way, you have to practice well. This is very important theorem. Please do copy in the notes and practice the same. So here is the next theorem. This theorem is also important. It is asked in 2019, but most of the times only statement is given directly. So Jordan decomposition theorem statement: a function f is defined on closed interval ab is of bounded variation if and only if it can be expressed as difference of two monotonically increasing functions on ab. So in the previous session we have proved that function of bounded if f is a monotone function, every monotonic function is a function of bounded variation. That is what we have proved. Here this theorem states that if f is bounded variation, if and only if it can be expressed as difference of two monotonically increasing functions on ab. Fine. So let me define a function. For the proof, let me define a function f from ab to r. As usual, bounded function it is. Meaning is f belongs to bounded variation of ab. That is f is bounded function. Fine. Let me define two functions, g as 1 by 2 into v f variation of f plus f, and h as 1 by 2 into variation of f minus f. That is addition and difference of the functions and along with this variation. And remember, where VF is none other than variation, that is function defined from AB to R in such a way that variation of F with reference to X is none other than total variation of X with A to X of a function F. Anyhow, it is given in the definition of total variation. You just go through this. If that was the case, we can write F as difference of G and H. So we can express F as a difference of G minus H. Now we have to prove that F is another than bounded function. G and H as, it is sufficient to prove that G and H are monotonically increasing function. That is the meaning, right? So every bounded variation can be expressed as difference of two monotonically increasing functions. Since F is bounded, we have assumed. Now it is enough to prove G and H are monotonically increasing. First, it is enough to prove for one function. Let me prove G is an increasing function. Increasing function. To prove this, let me consider two elements in an interval AB, in a closed interval. Let me take x1 and x2 are two elements in a closed interval AB in such a way that one is less than other. That is the meaning of increasing, right? So I have considered two variables in a interval such that one is less than another. Since it is given that f is belonging to bounded variation of AB, right? Here I have written f belongs to bounded variation of AB, implies that since x1 and x2 are elements of AB, I can write f belongs to bounded variation of x1 and x2 as well. Why? Because they are the elements of A and B. Then as per the definition of bounded variation, I can write f of x2, magnitude is important, magnitude of f of x2 minus f of x1 will be less than or equal to total variation from x1 to x2 of a function f. Further, we can split this just as we are using in integration. So just we can interchange. We can rewrite this as, see, I'll just rewrite this. I'm not going to simplify. I'm going to rewrite this as T total variation of x2 intermediate value A of f minus total variation of A of x1 of A. A is the intermediate value, so you can write x1 here, one and the same. So remember, whenever you have this term, we can rewrite like this. Now this is none other than variation, total variation of f with reference to x2 as per the definition, and this is none other than total variation of f with reference to x1 as per the definitions. Fine. So what we have arrived that f of x2 minus f, that is 0 is less than or equal to variation of x2 minus variation of x1, right? 0 is always less than or equal to this value. Why? Because it has some certain functions inside. So we can write equivalent of this statement is f of x1 is less than or equal to variation of f with reference to x2, right? Something like 6 minus 5 is, or else 0 less than or equal to 6 minus 5 is same as writing 5 is less than or equal to 6. That is what I have written here. See, every single statement is also having meaning, but it is abstract. You have to understand. Now, let me consider g of x2 minus g of x1. G of x2 minus g of x1 as 1 by 2 times vf of x2 minus vf of x1 in terms of variation. Why? Because I have defined g as variation of a function. So I can write with reference to x2 and x1. Plus again f is there, so I can write f of x2 minus f of x1. See, I have defined g as 1 by 2 into vf plus f. Since it is bounded variation with reference to x2 and x1, I am writing it. Since g of x2 we are subtracting the function, so I can write like this. And moreover, we can write that f of x2 minus f of x1, I mean magnitude of this value will be always less than or equal to variation of x2 minus variation of x1. Meaning is that whenever this term, that is second term, is less than or equal to first term, we can write that this value is greater than or equal to 0. Right? See, this is the second term, this is the first term. Second term is greater than or equal to, second term is less than or equal to first term, meaning is that this value is greater than 0. See, here 2 is less than, when you subtract 2 minus 1, you will get positive value only, right? Positive value meaning is greater than or equal to 0. Therefore, I can write g of x2 minus g of x1 is greater than or equal to 0. Why? Because when you subtract, you will get positive term only. Why? Because second term is lesser term compared to first term. When first term is highest, you will get positive value when you subtract. So, I can write that g of x2 minus g of x1 is greater than or equal to 0. I'll just write here g of x2 minus g of x1 is greater than or equal to 0. Meaning is it is increasing. that is G is increasing function. So we have proved that one function is increasing, that is G is increasing. Similarly, following the same procedure, we can prove that H is also increasing function. Fine, one part is we proved, that is we have assumed that F is bounded variation, that is function of bounded variation, and we have proved that G and H are increasing function. Now converse part we need to prove. Conversely, so this is a symbol for converse part. Conversely, suppose let me take F is equal to G minus H, that is difference of two function. G and H be monotonic, that is increasing function on AB. Now we have to prove that F is function of bounded variation, that is F belongs to bounded variation of AB. To prove that, we have to prove that this is function of bounded variation, converse part. Fine. So for that we have to assume, as per the definition of bounded variation, we should need a partition of a closed interval AB. F is always a function from AB to R, right, in case of bounded variation. Now I am going to divide this partition, this interval into partition in such a way that A is equal to x0 less than x1 less than x2. So if you keep on continuing, it will be less than xm. Let me take the end value of a closed interval AB. I have divided the partition. Now as per the definition of bounded variation, AB of f comma q, I can write variation definition as magnitude of f of xi minus f of xi minus 1. This is from the definition of function of bounded variation. Now I can write this as I is equal to 1 to m. In terms of G and H I am going to express. Why? Because I have taken f as G minus H. Similarly, f of xi I can write this as G of xi minus G of xi minus 1 minus h of xi minus h of xi minus 1. I have just simplified in one shot. See here, f of xi is g of xi minus h of xi. F of xi minus 1 is g of xi minus 1 minus h of xi minus 1. But I have grouped it in separate manner. That is g in one term and h as one term. Fine, if you want you can write it separately. Clear? Now I am going to split this magnitude for each and every term. So I can write less than or equal to, since we are splitting the magnitude. I is equal to 1 to m magnitude of g of xi minus g of xi minus 1 plus magnitude of h of xi. I am going to split the summation also. I is equal to 1 to m h of xi minus h of xi minus 1. Along with the magnitude, I have splitted the summation sign as well. Fine. Now, as per the proof that we have done just now, I can write the same as g of b minus g of a plus this is none other than h of b minus h of a. Why? Because xi and xi minus 1 are one of the partitions of a interval AB. Xi, you can clearly note that xi and xi minus 1 will be in between a and b. It is one of the partition. Xi is none other than, it is the highest value. I minus 1 is the lowest value. So b minus a. I can write this as g of b minus g of a. Anyhow, it is less than infinity. That is, it is finite quantity, right? This implies that it satisfies the definition of bounded variation, right? Is finite. It is enough to prove this is less than infinity. Is finite. This implies that f belongs to bounded variation of AB. So converse part also verified. Hence the proof. So this is the Jordan decomposition theorem. It says that if f is a bounded function, increasing functions. Fine. So this is the proof, and we have one corollary on this. It is very simple. So here is a corollary. If f is a function of bounded variation on AB, then f does exist almost everywhere on AB, closed interval AB. So here what is given? F is function of bounded variation. Meaning is f belongs to bounded variation of AB. Right? Then just now we have proved that from the theorem we can write f as difference of two increasing function g and h. So difference of two increasing function where g and h are increasing functions. G and h are increasing function. This is from above theorem. That is Jordan decomposition theorem, right? So above theorem I can write like this. Above theorem. Fine. Now by lebesque theorem, in the theorem what we have proved in the previous, that is before this theorem, I have proved one statement. No, there from the lebesque theorem g dash and h dash exist, right? So this is what I have proved. See the lebesque theorem, what it says: if f is an increasing and real valued function on AB, then f is differentiable. So if f is increasing and real valued, we can say f dash exists, right? See here, f is differentiable, and f G and H are increasing function. Therefore, by lebesque theorem, I can write that G dash and H dash exist almost everywhere on AB. So if G dash and H dash exist, since F can be expressed as G difference of G and H, therefore I can write F dash as G dash and H dash, which is exist almost everywhere on AB. That is what we require to prove this. Hence the corollary. Hope so it is clear for you. Further very important theorems will be there. In most of the question paper, almost maximum 2 to 3 questions will be asked from 4th unit only. So please don't neglect 4th unit. Do copy the notes, maintain the notes and practice the theorem so that you will understand the concept. Thank you.